Hi, I'm Ellie. I'm a fourth year engineering student at Durham University, and I've just finished a summer placement with the Durham Energy Institute. So today I'm going to present the key findings of my literature review and report on technologies for hydrogen fuel in aviation applications. So this is a quick outline of the topics I'm going to cover today. Okay, so why hydrogen? As can be seen from the graph, the air transport industry is responsible for 2.5% of global carbon emissions. When including other greenhouse gases such as nitrous oxides, water vapor, sulfur oxides, and harmful particulate emissions, this increases to around 5%. The aviation industry is predicted to increase by 4% each year. Even meeting targets for 1.5% improvements in efficiency, the aviation sector is still predicted to produce just under 2 gigatons of carbon dioxide in 2050. The only way to meet net zero targets by 2050 is through revolutionary technologies. There are three main pathways for hydrogen in the aviation industry. The first is through the use of hydrogen fuel cells. So these fuel cells use hydrogen and air to produce electricity. This electricity can then be used in two ways on an aircraft, either to power electric motors for propulsion or to supply auxiliary power to the aircraft. So this includes starting main engines, cabin air conditioning, and other electrical demands. For propulsive use, it is likely that new aircraft utilizing distributed propulsion, so multiple propellers, would be favored due to higher electrical and aerodynamic efficiencies. The second way is through hydrogen combustion. Hydrogen would be cryogenically stored as a liquid on board, then vaporized and passed through a combustion engine, followed by a fan to create thrust to propel the aircraft. Due to the higher energetic content of hydrogen, this option has the potential to dramatically reduce the fuel mass required for the same range when compared with kerosene. However, this method comes with significant changes required in infrastructure before it can be implemented, and is likely to be a long-term solution. However, Airbus only this Monday released their intention to develop 3 hydrogen combustion planes that they aim to put into service by 2035. The final way, and a possible drop-in solution for hydrogen, is to combine it with carbon dioxide to create a synthetic fuel similar to kerosene. If the electricity supplied to produce the hydrogen is from a renewable source, and the carbon dioxide is captured either from industry or directly from the air, this is a net zero solution, but still releases all the emissions associated with conventional air travel in the air and requires large amounts of energy to produce. Okay, so in terms of changes required for hydrogen applications in aviation, fuel cells for propulsion are likely to only be applicable for short-range flights. This includes the potential for new markets such as urban air taxis or microfeeders. For longer range flights using fuel cells, the weight of the fuel cell becomes prohibitive for propulsive applications, but is attractive for auxiliary power. For anything further than short range, hydrogen combustion engines are predicted to dominate. To fuel a plane with hydrogen, the volume required for the same energy as kerosene is 4 times greater even when condensed to a liquid. To accommodate this, revolutionary aircraft structures will be required to store larger amounts of fuel under cryogenic conditions. As previously mentioned, power-to-liquid creation of synthetic kerosene offers a drop-in but lower climate impact solution. For fuel cells and hydrogen combustion, changes to infrastructure is required. Refueling networks and procedures must be developed in order to enable a transition to hydrogen, and new plane designs will mean changes to airports in the long term. Okay, so there are still major technological challenges to overcome to enable hydrogen in aviation. For all three paths, scale and cost of hydrogen production are major barriers. Aviation may be able to take advantage of larger international shifts towards hydrogen economies to create economies of scale and standardization to reduce costs. As has always been a major challenge for aviation, weight is a large part of viability for technologies. Currently, the weight of both cryogenic storage containers and fuel cells mean that they are not viable for commercial aviation just yet. However, these are both expected to improve with increased investment in these areas from national and international research and development initiatives. Another challenge is that both fuel cell and combustion technologies do still create emissions. Scientific understanding is still unclear as to the extent of water vapor emissions on global warming potential, but legislation to optimize flight altitudes or new technologies may be able to help mitigate adverse effects. So in the short term, development in fuel cell power densities, particularly for polymer electrolyte membrane cells, could enable their use within the next decade for auxiliary power on board conventional aircraft. This could then move into propulsive technologies, providing a fuel cell powered plane by 2040. Hydrogen combustion for long-range flights is likely to be a long-term development requiring significant but necessary investment. Though there are significant challenges for the adoption of hydrogen technologies in aviation, it is a long-term investment in the absolute necessity of mitigating the climate impact of the aviation industry. I hope this has given you a quick overview of various pathways for hydrogen in aviation and their various applications based on literature analysis. You're able to find further information in my report. Thank you very much for listening.